Okay, so my slides are in English, and I will talk in English also. We will consider tilings of the plane by polygons. So assume that those polygons are given, and I say that we have a multi-set of polygons, meaning that some polygons of the same or from the set can have the same shape. So geometrically they are the same polygons, but we still distinguish them, for example, by putting colors on different polygons. And we consider tilings. A tiling is just a set of shifted polygons from the set, which are not overlapping, meaning that they do not share interior points, but they can share certain points on the border. And in that case, we require that if two polygons share a segment from their border, then they share the entire side. So this means side-to-side tilings.
And no rotation.
No rotation, no symmetries, I mean reflections, no reflections. Okay. And now I will define what means a substitution. So substitution is the main tool of constructing aperiodic families of tilings. We call a family of tilings aperiodic if all the tilings from that set have no periods. And we want the main goal of the main motivation of all I will say about is that we want to construct a family of tilings, and we want to define them by local rules. Here in my talk, the local rule is the following thing. We will assume that the sides of the polygons have color, and we are allowed to tile the plane only in such a way that the tiles are adjacent side to side, and the shared side have the same color in both polygons, adjacent polygons. So these are such types of local rules are called Van tiles. So originally Van tiles are tiles by squares, but we will also consider tiles by different shape, for example, triangles. The folklore theorem states that if all the tilings in the family are hierarchical, I will define later what does it mean. Then better to say that if a tiling is hierarchical, then it is aperiodic, non-periodic. So the main tool to design non-periodical tilings is by forcing a structure. So what does it mean, a structure? So the structure, the definition of a structure of hierarchical tilings is based on substitution. So a substitution is the following thing. Assume, for example, that we have three tiles, a triangle, another triangle, and a square. So substitution means that each of these polygons is cut into smaller polygons. In this case, each smaller polygon has size 1/5 of the original polygons. And all the parts obtained by this cut have the shape of the original tiles. So that means that each polygon from our set S is cut into polygons in the same, say S over 5 in this case. So this is one of the substitution. And another substitution is this gray one. Here we have only one shape of one square. So our set consists of one square. And this square is divided, is cut into 4 squares. And here, the last green-blue example is then we have in our set 2 squares. One of them is cut in green and 2 green and 2 blue, and another one is cut into 3 green and 1 blue. So now assume that a substitution is given. So a set of polygons is given, a substitution is given, and we want to define what means a hierarchy. So what that the tiling is hierarchical. That means the following. So every substitution defines the notion of decomposition of a tiling. This means the following. We have some, assume that we are given a tiling, say of the plane, of a part of the plane, and then we substitute each tile by the right hand side of the rule in the substitution. That means we just a cut of each tile. And the resulting tiling is denoted, is called decomposition. And the inverse operation is called composition. This is not a total operation because it might happen that there is no tiling whose decomposition equals to our tiling, so this is a partial operation. And also it might be that that some tiling have several compositions. And the next definition is the following one. So if we have a substitution, then the tilings in the right-hand side of the rules of the substitution are called macro tiles. And I will need also a notion, a more general notion of a super tile. Super tile is a tiling which is obtained from some original tile by applying decomposition several times. So if we apply it one time, then we call the resulting tile a macro tile, otherwise a super tile. So all macro tiles are also super tiles. Is it clear so far?
Yes.
Okay.
I have a question. So in previous slide, you give some examples. So are these open or closed tiles, the green and blue? So
Let's say closed.
Open. Closed, but then they don't have the same border in the big tile. And
I don't understand your.
So you said that if two borders overlap, they need to have the same color.
Right.
But then in the big tiles at the right, I see
these are not colored, Bruno. These are not colored tiles. I just
green and
colors,
blue are just two elements of a multi-set of tiles. So they are just shown by, they are different elements.
Okay.
These colors are just to distinguish different tiles of the same shape, and that's it.
Oh,
here
and I forgot, why do we repeat tiles in the set?
Because we want to distinguish them in the picture. So for no, geometrically it will be the same tile, but it will be a labeled configuration. And this is just this pattern formed by label is interesting. Is okay. What is interesting. It interests us.
Right.
Okay, then it's clear, everything.
Mm-hmm. And then the first main notion is a notion of a substitutional tiling. So we assume that a set of tiles is fixed, a substitution is fixed, and we call a tiling of a plane or of a part of the plane is substitutional if any its finite fragment occurs in a supertile. And there is a very close notion which called the notion of hierarchical tiling. And this means that the tiling admits countably many compositions. So it can be composed one time, then the resulting tiling can be composed the second time, and so on, infinitely many, an infinite chain of compositions. And one can show that every substitutional tiling is actually hierarchical. So we have two classes of tilings, a small one, a class of substitution tilings, and a larger one, that class of hierarchical tiling. In general case, these are different classes. And the folklore theorem states that every hierarchical tiling is aperiodical, assuming that we have the unique composition property. The unique composition property means that if a tiling has a composition, then it is unique. For example, this gray substitution doesn't have that property. We can tile the entire plane in such a way that it has 4 different compositions. For this green-blue composition substitution, I don't know actually if it has its property or not. And also I don't know if this property holds for the first substitution. And now I will define the second main notion of needed in my talk. So recall that the initial goal was to define by local rules. That means by just by coloring sides of the tiles, families of tilings which consist of only non-periodical tiling. And the first such family was defined using actually this substitution, this gray substitution. And this was done by Robinson and later refined by Durand, Shane, Levin. What does it mean? Based on that substitution, they define some colors on sides such that the following holds. Every correct tiling by this colored tile has the unique composition, which is again a correct tiling of the plane. And this implies that every tiling by those one tiles admits infinitely many decompositions and hence is aperiodic. And so the interesting question.
I have a question, sorry.
Right.
So we take some multi-set of polygons and color its sides.
Right.
And the same polygon can be colored in different way, and we obtain some different colored polygons, yeah?
Right, right,
okay,
exactly.
Okay.
Mm-hmm. Right. And now an interesting question is for which substitution that can be done. So we know that it holds for the gray substitution. And more specifically, we want, we are given some family of tilings. maybe periodical or not, doesn't matter. And we will call such a family sofic if the following holds. We can color initial tiles. When I say color, that means that we color their sides, so that a tiling with colored tiles is correct if and only if removing colors produces a tiling from the family. That means that we define our family, the initial family of tilings, using local rules of one type. So is this definition clear, Misha?
Yes, so the requirement is family of tilings means we fix multi-set of polygons.
Right.
And now we say the family is sofic if we can define it by these local rules. So by coloring the sides in some specific way, okay.
Right.
I see.
Right.
But what is written exactly is not good, because normally if you have an incorrect colored tile, you also can get by removing colors. If you just make colors, change the colors, and if then you get an incorrect tiling, colored tile, local rules are not true, but removing colors, we still get a tiling from the family. So you should not say like this.
Okay, maybe it's not correct. I will say it in more details. If a tiling belongs to the family, then we can color all the sides in those sides of that tiling in such a way that the resulting tiling by color with colored tiles satisfy all the rules, and all the tiles belong to our family of colored tiles. And the other way around, if we tile using our tiles the plane in the correct way, then after removing colors, we obtain a tiling of from our family. So that's what I intended to say.
Good.
Okay.
And each tiling from the family should be produced by the same coloring, or for different tilings we may use different coloring.
No,
I don't understand.
Tiling from the family have different colorings in general. It's not doesn't require to be unique, but it
Each tile may be colored in its own way. So if we have two identical tiles, we can color them in different ways. The only thing we want to have that the resulting colored tiles belong to our family of colored tiles.
My question was mainly about the universal quantifier. Each tiling from this family should be it is possible to color it and produce the correct tiling.
Right. For each tiling in the family, we find its coloring. Right.
And local rules may be different for different tilings.
Misha, local rules are fixed. This is one rules. So local rules claim, stipulate that tiles are adjacent only side to side, and the colors of the adjacent sides match. These are
okay. I meant that coloring maybe.
Colorings can differ, of course. Colorings may be different from different.
Local rule in this setting, yes, it is very simple. Just color of sides should be equal.
Yes. Okay. Now we have the following theorem. The main theorem of Goodman-Strauss states that under some mild conditions on substitution, the family of substitutional tilings is sofic. And a similar theorem was proven by Fernique and Ollinger, which is just the same theorem, but for hierarchical tilings. Under some mild conditions on substitution, the family of hierarchical tilings is sofic. Goodman-Strauss theorem has the paper of Goodman-Strauss has two versions, as a short version of 40 pages and the long version of 76 pages. And in both versions, he doesn't specify these mild conditions. So to say, the reader should extract these conditions from the proof. And I think that nobody was able to extract those conditions. However, I think that the proof is correct, and one can extract those substitutions so that to formulate the theorem explicitly. But I fear that those conditions will be very unnatural, and anyway, you can't verify the proof because it's long, and during verification you need to keep these conditions in your memory. You need somehow to memorize that, and that seems impossible. So that means that we have no explicit formulations of Goodman-Strauss theorem. And also Goodman-Strauss claims that the theorem of also the second theorem, but it doesn't appear in his paper. Okay, and for Fernique and Ollinger, the situation is much better. They formulate their conditions explicitly before proving the theorem. But I think that they have some mistakes in the formulation. But those mistakes can be fixed. And so one can obtain a theorem with explicit statement, formulation, and a proof that can be verified. And so in the sequel, I will restrict myself only to Fernique and Ollinger version of Goodman-Strauss theorem. Is this clear?
But it's useful to recall the definition of hierarchical tiling. It possesses infinitely many compositions.
Right, right. So if a tiling possesses infinitely many compositions, then we can color somehow the tiles so that to obtain the correct tiling of using our tile set, and the other way around. So if we have a correct tiling, then removing tiling, we obtain hierarchical tiling. So I succeeded to give formulations of both theorem, and we have also some 1 hour left. Then I can prove something. Actually, the choice is the following. I can prove something, or I can also state Fernique and Ollinger theorem in explicit way, defining those mild conditions. I think that it's better to prove something, because for Fernique and Ollinger, the conditions are also not very natural. So they come from their construction. And the construction is more interesting than the statement of the theorem. And the construction may be illustrated just by one example. And for that example is also non-trivial. And I will proceed to that example. So I will skip for now the formulation of Fernique and Ollinger and just illustrate their construction using one example. So here is the example. So consider the following substitution, which is sort of Robinson substitution, but a little bit more complicated. So a square is cut into 9 squares. And now let's just make our goal modest. We do not want to define, first of all, for this particular distribution, the statement is trivial because we have only one actually tiling of the set, and we do not need any colors to define this tiling. All this one tiling is trivially hierarchical, and we do not need any colors at all. So to illustrate the technique, let's change our goal a little bit. We want to color tiles, these squares, in such a way that every correct tiling has the unique composition. Why it's interesting? Because it means that the tiling by these colored tiles, any tiling by these colored tiles is non-periodic. So this produces a non-periodic family of tilings, and we will use such families are well known. For example, we can use Robinson construction, but we will use another construction which can be generalized for a large class of substitution. That's why it is interesting.
Yeah, one can say differently. So we have actually 9 tiles in our multi-set, which all are rectangles and all have the same decomposition. No?
We can, but in that case, we need to put the numbers. I have missed. I haven't done this.
It also no, sorry, it also won't be unique, you know. No, something is wrong here.
Okay, so I will now define a particular set of colored tiles, of one tiles. To this end, I will let's contemplate this picture. On the left, we can see the general tile of our set. It has first of all, for a moment, I will allow to put a number of tiles. We will later remove this number. This number T in the middle of the tile is called the type of the tile. And also we will have colors on site. Each color actually consists of 3 parts called indices. Blue index, green index, and red index. They are denoted by variables here, X, Y, and Z with index, with numbers, with subscripts. And this picture indicates how the substitution works on colored tiles. So the left tile is cut, is substituted by what is written in the on the right. On the right, you see that the macro tile consists of 9 tiles, and the numbers in the middle just indicates which is called the type, just indicates the position of the tile in the macro tile. So 1 means the left, upper left corner, and so on. 5 means the middle. Now, in the right-hand side,
why do you use such strange numbers? -1, 25.
So
69.
for 25, it's easy to explain. 25 stays on the border between 2 and 5. 23 on the border of 2 and 3, and so on. Now, why I use -1 and -2? I can use here any elements. So, for example, P and M. They should be just different from all the remaining indices. So these indices, red indices on the border, will enforce that the tiles, the macro tiles, are aligned in a proper way.
Mm-hmm. And what about variables? You have also some variables in the picture.
So in the what means variables? So
Z1, Z4.
So in the left, Z1 is either an element.
In the right. In the right.
This green Z1 is the same that red Z1 on the left. For example, if we have here 7 or 23, we have here also 23. Now, using the substitution, I will define later our tile set. More or less, this will be all the tiles on the right, which appear in macro tiles. Fernique and Ollinger define them, I mean our tile sets explicitly. More or less, they say the following: the tile number 2 must have identical green indices on the top and on the bottom, identical green indices on the left and on the right. Those will range from 1 to 9. They also define the range of x1 or of other 2 indices, and so on. But this definition is very complicated, and I couldn't memorize it. And then in the course of the proof, it is very hard to use this definition because you can't memorize it. And so I will define the same tile set, but in a different way. And here is the way I will use. So if, let's use some terminology. The left tile is called the parent of all 9 tiles on the right. And on the conversely, all these 9 tiles will be called children of the left-hand side, of the left tile. And here is the set of the tile set I will allow. So consider this particular tile. It has 5 in the middle. By the way, I forgot to say that we allow our variable are either elements of a specific set, which will be clear later. What is this set? Or they can be all just variables, just letters, x1, x2, x3. We allow both. Now, we will.
But it means that you have many tiles of this form. X1 can be, say,
some particular thing. For example, x1 can be 25.
Yes.
Or x1 will just x1, just the variable in our tiles. So if x1 is something particular, then, for example, child number 2 has also some particular x1 here. If x1 is a variable, then child number 2 has also variable here.
Okay.
Okay. So consider this particular tile, which has fixed red indices, and blue and green indices are just variables. And consider all its descendants. That means all its children, children of children, and so on. Actually, it's enough to have 4 iterations of this, but it's not important. Anyway, we will have some finite set of tiles, and that will be our tile set. So here on this picture, I have drawn some of these descendants. For example, in the bottom, in the upper left corner, we have some particular tile of type 1, which is actually the first child of the initial tile. For example, in the tile of type 5 in the upper left corner is the child number 5 of the child number 1 of the initial tile, and so on. On this picture, you can see that some tiles have indefinite indices, that is variable. Some of them are have only definite indices. And it's clear from this picture that all indices range over some fixed sets. Actually, we can consider only tiles with definite indexes, but this will be more complicated, and we will stick to the tile set to a larger tile set where we allow indefinite indexes. Misha, is it clear what is a tile set?
I hope yes.
Now, we will use some simple properties of this tile set. First of all, every tile in our tile set has a parent. And why is this? Misha, why is this?
We should somehow explain why this unique tile has a parent, because all other tiles...
The initial tile.
Yeah, with 5 in the middle.
Okay. This tile is its own parent. So that's simple. Let's see. Assume that we have here 5. Now consider this central tile. It has 45 on the left.
Please show the next slide with this. You have, yeah, okay.
You see?
Yeah.
So the property of this tile is that it is its own parent. And
yeah, but all
other
tiles have parents by definition.
Right. So that's why this tile is chosen as a, so to say, the initial tile. Okay. Now we will also need some other properties of our tile set, which were taken as definition of tile set, but now in my exposition these are just properties. For example, the first property considers tiles with of even type. Let's start with the property that the type of the tile is determined uniquely by red indices. So, for example, if we see that all the red indices have 5 inside them, then it's tile number 5. If 2 indices have 1, then it can be only tile number 1, and so on. So red indices determine the type. And that means that the type may be removed to obtain just the one tiles without any number in the middle. This is the first property. Misha?
Yeah, I'm follow.
Okay. The second property, the tiles of even type, the 2, 4, 6, and 8, have the property that green indices on the opposite sides are the same, right? Because of this property that all the tiles have parents. Now, these tiles 1, 3, 7, and 8, which are corner tiles, have also the following property. This index T will be called parential index because it indicates the type of the parent. So the parential index of the corner tiles determines uniquely all the other indices. And why is this? For example, consider tile, the corner tile number 1. Green indices are fixed, red indices are fixed, and Z1 and Z4 are defined uniquely using T, from T. And why is this? Recall that our tile has a parent, and the parent of this tile must have type T. But Z1 and Z4 are red indices of the type of this parential tile. And red indices are determined uniquely if we know the type. So on the left, Z1 and Z4 are defined uniquely from T, and hence on the right, for the tile, for the child number 1, Z1 and Z4, the other two green indices are defined uniquely from T, from the other two indices.
I don't understand it. In the left tile, you have 4 independent variables, x1, x2, and so on. Why you can x2 and x3 can differ, actually?
Sure. But Z1 and Z4 are fixed. They are fixed if we fix T. Look to this end. Look on the right. If you know the position of the tile, that it's its type, you know also all red indices, right?
Yeah.
Okay. Look then on the left. If you know T, you know Z1 and Z4.
Yes, but
and then look on the right again. On the look again on the right.
I see. Z1 and Z4, but it depends not on T, but on the red indices in the parent.
Right, but the red indices are in the parent are determined by T. In our tile set, it has the property that
green T in the right and black T in the left are the same.
Sure, they are the same.
It was unclear to me. Yeah, now I see it.
So far, we don't need any other properties of our tile set for the moment. So we have defined a tile set, and we have seen some of its properties. Okay, now we can proceed to prove our claim. So what do we want? First, we want first of all, we want that our tile set is non-trivial in the set that we can tile the entire plane by it. But that's a common thing. We take we consider super tiles, and super tiles. First of all, this is stated here explicitly. Theorem, the first easy theorem has two items. The decomposition of any correct tiling is a correct tiling. Let's see why is this. So assume that we have a tiling of the set by such a tiles, and then we substitute each such tile by this square 3 by 3. First of all, we have matching colors on all the internal sides. This is easily verified looking at the right-hand side, right, Misha?
Not easily, but
It's a short verification. So
yeah.
in the middle, everything. So this T, green T, Tama says that it гуляет on along this macro tile, and also red indices match, green indices match, and this green x1 and so on. Right?
Yeah. It seems quite natural, but there are some variants, and you should look through.
Now, what we need to prove else to prove that the decomposition of a correct tiling is a correct tiling? Assume that we have two matching tiles on the left. For example, assume they match, they are adjacent using the upper side. That means that they have the same indices here on the bottom and on the top. Now you see that what we have on the top of the macro tiles is a function of what was on the top of the tile, right?
Yes.
We just copy Z1, Y1, X1.
Yes.
And that means that if we have matched colors, then we have again matched colors, right?
But we need the same property for the bottom side.
Right. So look at the bottom side.
Yeah.
We have the same, exactly the same substitution of colors on the bottom.
But sorry. Suppose you consider one particular tile of the tiling, but let's imagine the next tile up to this particular one.
Okay.
But by condition, you should have in the bottom you should have y1, x1, z1.
Right.
And when we
apply the substitution,
we produce what? We produce z3, y3.
Right. And z3 is equal to z1, right?
Why?
Because on the upper in the upper tile, we have red Z3, which is actually equal to Z1. Because they match.
I see. We should take into account that we have equalities. red Z1 equals red Z3, green
from
X1.
the upper tile.
Yeah. For the upper tile. Yeah. I see. And actually, these equalities maintains in the right picture. Yeah. I see. And we should check it for all sides.
Right. But on the left, we have the same.
Yeah. I see.
Of colors.
I see. The argument is the same. We should just look through the picture. Picture is complicated.
It's a finite verification.
Finite verification.
And just
I
believe
agree.
me that there is no error here. There's no cheating here.
Okay.
Okay. Now we have the second item of the easy theorem. The composition of any correct tiling, if it exists, first is unique and is correct. And why is this? Why it is unique? Because if we see, for example, tile of type 1, then we know which tiles, how it, where, in which macro tiles it can fit. Because these indices 1, 2, and 1, 4 indicates that we need to have a tile of type 2 to the right. Tile.
Yeah.
So red indexes.
It's much simpler. Yeah.
Red indexes enforce the unique composition property. First of all. Second, when we define the transformation of colors from a tile to a macro tile, we keep all the indices. Look, we keep X1, we keep Y1, and also keep Z1 as green index. And that means that if two macro tiles, first of all, in our tiling, decomposed tiling, we know that the colors match. And that means that these macro tiles fit are so to some adjacent macro tile to macro side. And we know that Z1 matches Z1, X1 matches X1, Y1 matches Y1. And that means that in the initial tiling, also the colors match, all the three indexes match. And that's because we keep in the specific places all the three indexes. So if they match in the decomposition, then they match also in the original tiling. Okay, so this is also an easy part. So the first item implies that our tile set can tile the entire plane, because we can consider the initial decomposition. Decomposition is decomposition, and we will obtain a sequence of correct tilings, and that sequence can be used to tile the entire plane. It's a usual argument. Now, we also know that the composition of any correct tiling, if it exists, is unique and correct. So the only thing now that we need to prove is that there is such a composition. So the second theorem states that every correct tiling has a composition. And that's the hard thing. And if we prove this hard theorem, then we are done. Because now we will know then that every correct tiling has a composition. That composition is unique and it is correct by the previous theorem. Then it has again a composition which is unique and correct, and so on. So we will obtain that any correct tiling can be composed infinitely many times, and hence is hierarchical. So I think that is anybody who still catch with me?
Yes.
Yes.
Okay, good.
Yes.
So now you need to be brave, have courage to proceed to the hard part. So let's proceed to the hard part. So I divided hard part into two lemmas. Let's switch again first to our picture, the main picture. So assume that we have tiling, say, of the entire plane using our tiles. Then the red indices enforce that they are grouped into squares 3 by 3. However, they do not enforce yet that these squares are images of our tiles, just squares which looks like the macro tiles. And we need to prove actually that they are macro tiles. That's our goal. Because if we prove it, we prove that our tile has a composition. Actually, the composition, because it's unique. Okay, so once again, consider such a group of 9 tiles. What do we need to prove? We need to prove that there is a tile in our tile set on the left which produces this square, this sort of so-called pseudo macro tile. So now I claim that that tile is actually defined uniquely. So we have no choice for the parent, common parent of all 9 tiles. Let's see why. So why its type is uniquely determined? Misha, do you see why?
Sorry, what tile is uniquely determined?
We are looking for a tile on the left,
Yes.
which produces our pseudo macro tile.
Yeah.
I claim that that tile is uniquely determined. Maybe it's
by what?
By that square.
By the right hand side, it's
by
quite
the
clear.
Right hand side. So
It's quite clear.
Why it's clear?
Because we have discussed that variables on the top side allow to restore the variables on the top side. On the left side, the same. And so on and so on.
And what about T?
And what about T? T is determined by this. It appears many times. Actually, it appears on this. So how to say it? A circle.
On the circle. T appears on the circle first of all, and also T is defined by red. Uniquely by red indices.
Yes. Also, it's also uniquely defined by red.
Right. So we have no choice, but we need to prove that that choice, that unique tile, is in our tile set, and this is the non-trivial statement. We need to prove this. First of all, let's define this tile.
What is our goal? As I understand, you are going to prove that there is some coloring. So if
no, Misha, we have now a more modest goal. We do not want to define by colors hierarchical, all the hierarchical tilings. We just want to prove that any correct tiling has a composition. This is our goal. So imagine a correct tiling. We want to prove that it has a composition, and that's it. So we know that in this correct square, all the tiles have the same parent index, and that parent index should be in the middle of the salt tile, first of all. And also, let's see on the central tile, all the blue and green indices of our tile should be the same as the blue and green indices of the central tile. That's a more easy way to define that unique tile. Let's call this sequence sequence of green and blue indices the global contour of our tile. So our tile has a known global contour, which is inherited from the central tile. It has the known type, which is obtained from the parential index of all these tiles. And the red indices are defined by the type uniquely. And we need to prove that this tile is in our tile set. So why it's not easy and not obvious? Because we have taken a tile of our set from our tile set, I mean the central tile, but then we have changed its type. So it might be that such change produces a tile outside our tile set. We need to prove that it's impossible.
I don't understand.
Okay. This tile, which we are looking for, must be obtained from the central tile, right? By changing its type and also red indexes, right?
Okay, but actually, you are trying to define a composition.
Right.
And actually, from the previous notes, we know should form this picture 1, 2, 3, 4, 5, 6. Because it's the only way to produce them.
Okay.
And so why do we need to consider only this tile? We know its neighbors. This one, this one, this one, and T is written on all 8 neighbors.
Misha, again, so what I have said so far is a simple thing, that we are looking for a very specific tile, that one. And this is the only our option. And we need to prove 2 things, that this tile is in our set, and also that applying the substitution to this tile, we obtain indeed our square 3 by 3. Do you agree with that?
Yes.
So the second claim is easy. If we take this tile and apply to it a substitution, we will obtain exactly our square. Why is this? We will obtain a third middle tile, right? Central tile. we will obtain the third tiles of even type, second, fourth, because, and also we will obtain the third tiles of the corner, which is not obvious. And why is this? And that's because in our tile set, for the corner tiles, all the indices are defined by their type, by their differential indices, by this T. And T will be correct as wanted. And hence,
but why it is true? We have Z1, Z4, but Z2 and Z3. How we define them from the right tile?
So in our tile set, if we know T, we know also Z1 and Z4. And Z1 and Z4 are defined in such a way from T that if we apply a substitution to any tile,
I see. Actually, in substitution, red variables are changed by constants. And it's important, so yeah, we can restore them.
So if we apply a substitution to this tile, we obtain exactly what we want. But we still need to prove that this tile belongs to our tile set. Let's use the following definition. Two tiles are similar if they have the same global contour. That means that all blue and green indices are the same on all the sides. And using this terminology, we can say that we want to prove that this central tile is similar to a tile of type T. So if our central tile is surrounded by 6 tiles of the type differential index T, then it is similar to a type T tile. That's what we need to prove. Okay. And now let's relax our requirement of similarity. Fix a side of the tile. Then we will say that two tiles are similar with respect to a certain side, for example, upper side, if they have the same green and blue indices on that particular side. This is the relaxation. And then we need two theorems. There are two lemmas. The neighborhood lemma claims the following thing. Let a square of size 3 by 3 be tiled correctly by our tiles from our set, and A be its central tile. And assume also that the parent indices of all tiles from the square are equal to T. Then, with respect to each side, the tile A is similar to some type T tile, and that tile may depend on the side. So, with respect to the upper side, it's similar to one tile type of type. So, assuming that our tile is encircled, surrounded by tiles of differential index T, we can deduce from that it is similar in a relaxed way with respect to each side to a certain type T tile. And the second lemma, called duck lemma, says that if this relaxation happens, so if the conclusion of this theorem happens, then our tile is actually similar with respect to all sides to the same type T tile. And the composition of these lemmas yields the desired property. So our central tile is surrounded by tiles with potential index T, and hence it's similar to a type T tile with respect to all sides, and that's what we want to prove.
And actually, we have partially proved these lemmas.
Actually, no, we haven't proved any of these lemmas.
Yeah.
No. I think that we will skip the proof of the first lemma. It's actually simple by it requires. Maybe we will. So let's skip it for a moment, and let's consider the duck lemma. And the duck lemma is actually has the property 0 or nothing. Why is this? It actually claims that either if we have a tile from our set A, say, and a number T, that either we can point to a side on which A is not similar to any type T tile, or it's similar to some T-type tile, the same T-type line with respect to all sides. And this can be easily seen on our picture. So our picture with this one. On this picture, we can see that the blue and green indexes are very different in different tiles. For example, assume that our tile has type 1, and we want to distinguish it from all the tiles except tile number 5, the middle tile. So the middle tile can actually have all possible global contours, and that means for the middle tile we have the second alternative. So tile 1 is similar to the middle tile, to some middle tile, but it is different from all other tiles. And why is this? Look at the tiles, for example, 1 and 2. We can see that tile number 1 is different from tile number 2 in blue index on the right side, because tile number 1 has 12 and that other tile has 23. It is different from tile number 3 because the tile number on the same side. So whatever pair of tiles you choose, you can point to a place in the first tile where it is different from any tiles of the second tile type.
Mm-hmm.
Now, let's verify, for example, for why 1 is different, say, from 4. Misha, you see how to distinguish 1 from 4?
By what side? Right side? But right side,
some side.
Some side.
Take
right side. We have red 12 and
no. You can't use red indices. Only blue or
only blue or sorry. Then we have 14 and 47 on the bottom.
Wait. Right. 1 is different from 4 because we can choose 14 and 47, right?
Yeah.
Okay, how does this distinguish, say, in the opposite direction, 4 from 1? Which index to choose in 4, which is definitely different from 1?
The same bottom sides, but actually top sides also
14 and 0 we can choose also.
Okay, now more difficult task. How to distinguish 4 from 2?
-2 and 14. Right.
No, you
Or
can't
we
use -2.
no without red indices.
Only blue and green. That's important. Actually, it's enough to use only blue. How to distinguish 4 from 2 using blue indices? You need to point on the you are given at a tile of type 4, and you need, looking at that tile, you need to choose its side which distinguishes it from any tile of type 2.
It's not clear.
Okay, it's not clear.
Yeah,
It's a puzzle.
We have Y4, identical Y4 for the 4 tile.
Yes.
And for 2 tile, they're different.
If this Y4 is 12, then you can use the right-hand side. If this Y4 is 23, we can use the left side. And if it's different from both, we can use either side.
Yes. Yes.
You see, that the idea here is that all the tiles of different types is very different, and that's why we can distinguish them. And for the tile number 5, it can inherit actually all the contours, and for it we will have the second option. If the initial tile is a tile of number 5, sorry. Okay, I'm tired now, and anyway, the time is expired.
Almost over, yeah.
Okay, so the proof is based on these 2 lemmas. The second lemma can be easily verified looking at the picture, and the first one is also simple, but I think that it's hard to get it now.
Can you explain the name of the second lemma?
The name comes from the proverb: if you squeak like a duck, if you walk like a duck, if you fly like a duck, then you are possibly a duck. Is it?
Yeah. Okay. Okay.
Does it well?
Makes sense. Yes.
Makes sense. Okay. Okay, let's stop here. Thank you. Questions? So everybody is so puzzled that there are no questions. Maybe that's a good end of my talk. Ну, мы тогда закончим.
Да, думаю, да.
Угу.
До свидания. Спасибо за
свидания.
доклад.
Спасибо, спасибо.